Hello, my name is Tyan Hong, and this is my Lab 3 for Physics 2211. Using Newton's second law and the gravitational force formula, we will find the unknown mass of the black hole, then use this mass to create a trajectory of a spaceship, and determine the initial velocity that the ship must have to avoid crashing onto the planet or being sucked into the black hole at launch. We will be using a starter code and glow script to generate a computer modeling the motion of the orbiting star in part 1 and the motion of the spaceship launched from the planet in part 2. To briefly summarize the results, in part 1 we found the mass of the black hole to be 9.7 times e to the 33 kilograms, the magnitude of the net force to be 8.5 times e to the 28 newtons, the magnitude of the net force parallel to momentum to be 3.1 times e to the 28 newtons, and the perpendicular component of net force to be 7.9 e to the 28 newtons. In part 2, we found that the ship would need an initial velocity of -5 times e to the 7 meters per second in the x direction, and an initial velocity of 3 times e to the 6 meters per second in the y direction. Newton's second law, also known as the momentum principle, draws the relationship between force and momentum. Net force is equivalent to the change in momentum over a change in time. This equation is significant because it relates physical observations of the system to its surroundings, which can then be used to predict the motion of the object in the future. Net force can also be broken down into its perpendicular and parallel components. Therefore, the change in momentum over time can also be split into its perpendicular and parallel components. The parallel force changes the magnitude of the momentum, and the force perpendicular to momentum changes the direction of the momentum. Delta P over delta T times P hat is parallel to the momentum, and P times delta P hat over delta T is perpendicular to momentum. The gravitational force between two objects is equal to the universal gravitational constant, given by 6.7 times 10 to the negative 11, times the mass of the two objects divided by the squared distance between the objects. To find the mass of the black hole, the gravitational force formula can be rearranged so that m1 is equal to net force times the distance squared divided by the gravitational constant times the mass of object 2. In part 1, the system is the star and the surrounding is the black hole. In part 2, the system is the spaceship and the surrounding is the black hole plus the planet. In part 1, we will generate a model on glow script that models the orbit of the star around the black hole to find the unknown mass of the black hole. In part 2, we will generate a model on glow script that models the motion of the planet and the spaceship around the black hole to find the initial velocity that allows the spaceship to fly as close to the black hole as possible without crashing onto the planet or getting sucked in. In part 1, to create a model simulating the star around the black hole, I had to update the glow script starter code by first adding the mass of the star and delta T. In the calculation loop, I also updated the initial and final momentum variables using the mass of the star and the star's start and end velocity. Using this, I could then compute the net force and the change in momentum over time using Newton's second law, then find the perpendicular and parallel components for the force and the change in momentum over time. Finally, I used the rearranged gravitational force formula from earlier to calculate the average mass of the black hole. From the model, I found the average mass of the black hole to be 9.7 times e to the 33 kilograms, and the magnitude of net force to be equal to 8.5 times e to the 28 newtons. In order to create a model simulating the motion of the planet and the spaceship around the black hole, I had to update the glow script starter code by first adding the average mass of the black hole found in part 1. I was given the following constants: the universal gravitational constant, the mass of the planet, the mass of the ship, delta T, and the initial time. Using the momentum principle and the formula for gravitational force, I could find the net force on the planet and the ship to predict their trajectories. I also changed the initial velocity with each run and through trial and error found that an initial velocity of -5 times e to the 7 meters per second in the x direction and 3 times e to the 6 meters per second in the y direction allowed the ship to avoid crashing or being sucked into the black hole. These are the two glow script models generated. A potential source of error for this lab is the fact that we estimated the mass of the black hole by taking an average of the values found by the model in part 1, and therefore the estimated value for the mass of the black hole used in part 2 may not have been entirely accurate. Rounding errors could also contribute. What does this mean? How is net force and its parallel and perpendicular components different from the rate of change in momentum and its parallel and perpendicular components? Mathematically, net force and the change in momentum over time are equivalent according to Newton's second law. However, the only difference is that delta P over delta T can be calculated as a function of time using velocity and mass, which are either directly given or can be observed in the physical world. However, in this lab, F net cannot be directly calculated because the black hole's mass is initially unknown. Instead, we can deduce net force from its relationship with momentum. What initial velocity would you need to enter an orbit around the black hole? Through trial and error, I found that an initial launch velocity of -1 e5 8.5 e6 meters per second would allow the spaceship to orbit the black hole without being sucked in.